Good evening, everyone. I hope you are having a terrific Tuesday. Hi, guys. Did you miss me? Well, today is Tuesday and we are within our high school month. But guess what? Just because it's called high school month doesn't mean you have to be a high schooler. This month is strictly and specifically for all subjects that you look and see when you get ready to go into high school. So if you are an advanced learner, you want to learn more about math because you love math like I do, or you're advancing into high school, or you're a parent of a advanced learner, or want to be an advanced learner yourself, as well as an advanced high schooler. All of those are encompassed in this month. So if you want to know it, I am here to teach it, okay? So this week, today is geometry day 1. What we are learning are basic and key components of geometry. Of course, if you have any questions, you can comment that below. Any questions? All questions are important because if you have any questions, I am here to help. So to get us started, please click. You can click like, click heart, thumbs up. Let me know that you can hear me, and we can get started. Thank you. Let's get started. All right, you guys, we are going to learn and deal with inductive reasoning and deductive reasoning. Um, Inductive reasoning is the process of teaching a general conclusion by examining specific examples. So let's start off with the basics, because when you figure out what inductive reasoning is, you're gonna be like, oh, I know what that is. So remember skip counting when you said 3, 6, 9, 12, 15, and then the question will ask, okay, what is the next three? What is the next three numbers? And of course, the next three numbers would be 18, 21, and 24, right? Now, inductive reasoning say that, hey, I know that the next three numbers are 18, 21, and 24 because I can conclude that from the first number to the last number, I am adding 3, or I am doing multiples of 3. So inductive reasoning is the process of teaching a general conclusion or reaching a general conclusion by examining specific examples. So you have a specific example in your inductive reasoning when you can see within that you are with skip counting, you know that, hey, I'm adding 3 to each number, therefore I know the next three numbers are 18, 21, 24. And then if I want to continue on, I know that in my inductive reasoning, I know that my conclusion is I'm adding 3, so I can solve my answers or find my answers by adding 3. Any questions on inductive reasoning? Because that's really all it is. You can use it to predict a number. You can use it to make a conjecture. Um, like it says, consider picking a number, multiply the number by 8, add 6 to that answer, divide the sum by 2, and then subtract 3. So now, say for instance, your original number is 5 based on that question, because we're going to do inductive reasoning to use inductive reasoning to make a conjunction. So the question we had was, consider the following procedure. Pick a number. The number I pick is 5. With that 5, I'm going to multiply it by 8. So then multiply by 8, that gives me 40. Then I take the sum, well, that's 40. The other one looks like an open 6. Then once I multiply the number by 8, then I can add 6, and that gives me 46. Then after I add, I divide it by 2, so 46 divided by 2, that gives me 23. And then, of course, I take the 23 and I subtract it by 3 because that is what the question required. So 23 minus 3, that equals 20. So we started with 5, and then following the procedure produced 20. So if I start my procedure correctly with another number, then say for instance we started with 6, then we should produce a final result of 24. Then if I do 10, I should have a result of 100. So so in these cases, we are learning that the number is 4 times the original number. So based on what we're seeing is if I put new numbers in, it is 4 times the original number. So if you put in 100, well, you put in 10, you'll get 40. You put in 5, you'll get 20. You put in 100, you'll get 400. And so each number, we can conjure that based on the procedure or inductive reasoning, we conjure or have the inductive reasoning. Based on that, the results of the answer is always 4 times the original number. So literally, you can easily say that, hey, if I was making a table of numbers and based on a procedure, my input was 5, my output came out to be 20. Then my next input was 6, and my output was 40. And as you put in your input, it allows your output to be 4 times the original number. So with inductive reasoning, it allows you to predict a number, and it also allows you to make a conjecture, meaning a conscious decision on or come to a conclusion or reasoning on the original number to the result number. Any questions on this? Any questions on inductive reasoning at all? Now, sometimes in inductive reasoning, you'll have things called a counter example. And in geometry, The counter example could be just one example. You don't need 1,000. You just need one example that can disprove what you're asking. So say for instance, you do x is greater than 0. A counter example would be where the absolute value of 0 greater than 0, and then you have 0 is greater than 0. Well, we know 0 is not greater than 0. 0 equals 0. Now, had this been greater or equal to 0, then it couldn't be disproved. But because I was able to find one counter example, it takes my statement and it takes my true statement and make it false. Another example would be x squared is greater than x. Well, a counter example of that would be 1 squared greater than 1, 1 greater than 1. Well, we know that the true statement says the first term should be greater than is greater than the second term. Well, we know 1 is not greater than 1. 1 is equal to 1. Had the equation been greater than equal to, it still would have been a true statement. But because it's not greater than equal to and it's just greater, this makes the counterexample makes my original statement that should have been a true statement false. Another example, the square root of x squared equals x. A good example would be the square root of -3 squared equals -3. Well, we know that within the square root, you must first do the squared. So then you have the square root, the exponent. So -3 squared, that is square root of 9 equals -3. And then the square root of 9, that equals 3 and -3. Now, based on the original statement, the counterexample has proved that this is false because we know that the square root of really any number will not be negative, because you can't take the square root of a negative unless you want an imaginary number. Any questions on counter examples? All right, moving on. We have deductive reasoning. Deductive reasoning is different than Inductive reasoning. Deductive reasoning is the process of reaching a conclusion by applying general assumptions, procedures, or principles. Now, what that simply means is based on procedure, I can deduct, or based on the assumption of what I am given, I can deduct. Based on the principle of the equation, I can deduct. So, deductive reason is easily saying, hey, based on this specific assumption, this specific procedure, this specific principle, I can conclude based on deductive reasoning. For example, procedure. It says use use deductive reasoning to establish a conjunction. Now remember, inductive reasoning allowed us to make sure I say that correctly. Inductive reason allowed us to make a conjunction. Deductive reason allows us to establish the conjunction, meaning you're going to make an equation based off of this. So, procedure says pick a number, multiply the number by 8, add 6 to the product, divide it by 2, and subtract 3. So now, originally we actually picked an actual number. This time we're not picking a number. What we're doing is making a deduction based off of what we learned. So n is my number. I multiply n to 8, and that gives me 8n. I then add 6 to my 8n, and of course that gives me 8n plus 6. Then I take that 8n and I divide it by 2. Once I divide each term by 2, that leaves me with 8n, that leaves me with 4n plus 3. Then once I subtract 3 from my equation, what I am left with is 4n. So we have established the conjuncture that a number that is picked, that is multiplied by 8, and added 6 to it, divide the answer by 2, and then subtract 3 from it. Once you do that, your deductive reason conclusion says that my example produces a number that is 4 times the original number. So always remember, inductive, it makes a conjuncture, whereas deductive establishes the conjuncture. So inductive, you are picking a number, whereas deductive, you're establishing a set or establishing a rule based on the assumption and the conclusion, the assumptions, the principles, and the procedures of what is being requested of you. Any questions on inductive counterexample or deductive reasoning? All right, next up we have problem-solving strategies. In this example, there's something called the polyus, and I'm probably pronouncing it wrong. So if I am, please text me and let me know exactly how to pronounce this name. It is based off of George Polya. Is a mathematician who made a study of problem solving. So he has a 4-step problem solving strategy which helps you strategize on how to solve your problem. So the first thing you do is understand the problem. You must have a clear understanding of the problem. To help you focus on understanding the problem, you must consider these questions. Can you restate the problem in your own words? Can you determine what is known about these types of problems? Is there missing information that, if known, would allow you to solve the problem? Is there extraneous information that is not needed to solve the problem? And what is the goal? So, first step is understand the problem. Make sure you have clear understanding of what the problem is asking you. That's number one. Number two, devise a plan. Now, this is really good for those who are making decisions based on a problem. This is also good for when you are working on word problems. For those of you who struggle with word problems, this is the best strategy for word problems, and it's introduced in geometry as well. So now, devise a plan. Successful problem solvers use a variety of techniques when they attempt to solve a problem. Here are some frequently used procedures. You can make a list of the known information. You can make a list of information that is needed. You can draw a diagram, which usually is a Venn diagram like so. You can make an organized list that shows all the possibilities. You can make a table or a chart. And of course, a table can look like this, or you can make a chart, which typically looks like this. You can work backwards, like if you know how to get to the answer, but you don't know the exact steps, you can start from the answer and work your way backwards to get to the point where you get stuck. Try to solve a simpler or more a simpler problem, meaning tries a problem that's not as difficult and then progress to the actual problem. Look for a pattern. That's very great for when you're doing inductive reasoning. Look for a pattern. Write an equation if necessary. Define what each variable represents. So, say for instance, I know that When you're trying to find the break even in a business, you have R, which is the revenue. And then you have C for cost. And within cost, you have FC, which is the fixed cost. And of course, with the fixed cost, allows you is flat rate, is what you're going to pay regardless. Because a cost, of course, is your expenses. Revenues is the money that's coming in. Cost is what the money going out. So fixed cost is the flat money that you have to pay. That could be insurance. That could be car notes, all that good stuff. All that encompasses your business. Then VC is your variable cost. And VC is typically when you see something per hour or per minute or per use. That is considered a variable cost. And variable costs will allow you to, it fluctuates your expenses depending on how it is calculated. So say for instance, your lights are $10, your electric bill is based off of how many kilowatts you pay for during the month, and the kilowatts cost $10. So then it'll be 10 kW because it's $10 per kilowatt. So say for instance you have energy of 20 kilowatts within your business. So that means you would take that for the month. So then you'll take that 10 multiplied by 20, and your variable cost for lights would be $200. And so this is what they mean when they say write an equation if necessary and define what each variable represents. Just an example for that. Also, perform an experiment. Guess at a solution and then check your result, which that works for when you're doing estimations and rounding. And then use indirect reasoning, meaning making a roundabout way of figuring your answer out. And that is all for devise a plan. Next, we have carry out your plan. Once you make that plan, carry it out to every piece of what you made the plan to be. Once you've came up with the plan, you cannot change what goes on with this plan. You must follow through with your plan. Now, will you have to make adjustments once you complete your plan? Yes. But carrying out the plan, that is not when you do it. You make the adjustment after you reach your results of carrying out your plan. So, how do you carry out the plan? You must make sure you work carefully. You must make sure you keep an accurate and neat record of all your attempts of your plan. You must realize that some of your initial plans will not work and that you may have to devise another plan or modify your existing plan once you have your results. Then, after you have devised and carried out the plan, then you must review the solution. Reviewing the solution when you found it is all you have to do is check the solution. So, how do you check the solution? Ensure the solution is consistent with the facts of the problem, meaning it checks off the problem's information. Then, interpret the solution in the context of the problem, meaning based on your given information, your conclusion should include the given information. Then, after whether there are generalizations of the solution that could apply to other problems. So what that means is, can this solution be applied to other areas of the problem that you have? So of the problem, can this solution not only be used for your problem, but the other problem for more problems to come, or problems after you and beyond you. So I find this as a great strategy for studying, especially when you're trying to execute out a plan on how to study. This is one of the ways that I use as my strategy on how I learn how to study. Any questions on problem solving strategy? Also, if you are just now tuning in and you want to review what we are learning, the YouTube link is listed in the description below, Facebookers. So all you have to do is click on that YouTube link. You should see the live going on strong. Once you click on that, you can either double tap to the left or you can drag it from the red bar and you can drag it all the way back to review and rewind what we're learning today, okay? And of course, if you still have any questions on what we're doing today, please list them in the comments below. Okay, moving on to sets. S-E-T-S, sets. All right. In an attempt to better understand the universe, ancient astronomers, people who look at the stars, classified certain groups of stars as constellations. And today we still find it extremely helpful to classify things into groups that enables us to find order and meaning in a complicated world. So, any group or collection of objects is called a set. So, the seasons, spring, summer, fall, and winter. That is considered a set. A group or collection of objects. A, B, C, D, E, F. A group of letters. Ball, doll, cars, blocks. That is considered a set. And within that set, each individual word, letter, or object, that is called an element or member of the set. So when you are doing sets, you're going to see different things about them that's going to ask different questions. You're going to see things such as the universe. You're going to see things such as a subset, a proper subset, a complement. And no, complement in this situation is different than any complement you have ever heard of. It's even spelt different. The complement that I'm focusing on has an E where the I should be. So let's get started on sets. So, working definition for the cardinality of a set. A cardinality of a set simply means how many elements in a set. So say the set of J equals 2, 5. If I ask you what is the cardinality of that set, I'm simply asking you how many elements are in the set. Well, we know that elements are each number, each object, each thing that is within the set. So 2 and 5 are elements in the set. So there are 2 elements in this set. Say, for instance, I have the season or S set of, bring this up a bit, move it over just a tad, of spring, summer, fall, and winter. So in this set, we have 1, 2, 3, 4 elements. Therefore, the cardinality or the number of elements in this set is 4. So in geometry, you will see something that says the cardinality of a set. All it means is how many elements, how many objects, how many things are in this set. Now, equal sets. Equal sets simply mean set A is equal to set B, where A equals B if and only if A and B have exactly the same elements. So, if A is the set of natural numbers to the set of counting numbers, and it's based off of coins, this is what it would look like. So natural numbers, meaning numbers of order, the nickel would go first, then the dime, then the quarter. And the counting numbers means that the dime goes first, because typically when you're counting, you learn how to count by tens, then by 25s, and sometimes by fives. Depending on how you count, it's really up to you. But for the example, they have dime, quarter, and nickel. So what it's saying is no matter what order this is in, they are equal sets because they have the exact same elements. So nickel, dime, quarter, nickel, no matter which way you spin it, if set A have the exact same element or same things as set B, it is called an equal set. And you can say it's an equal set by simply just saying A equals B. Any questions on equal sets? All right, moving on to the universal set. Universal set and the complement set. Now, universal set simply is all the elements in one set. Universal set is all the elements in one set. So universal set says, hey, these are all the numbers in the set. If you have a Venn diagram, this portion, this area right here, is called the universal set. It's also part of the complement set, because usually the complement is everything that's in the universe that's not in a set. And here's what I mean. Say, for instance, the universe set is 1, 2, 3, 4, 5. Set A is 1, 3, and 5. So the complement of A is everything that's in the universe that's not in set A. So what does that look like? Well, first, the complement of A is usually denoted as either A with a little c or A with an apostrophe, depending on how your teacher notates it. More than likely, you'll see it with a C more so than with the apostrophe. But again, it all depends on how your teacher denotes it. Okay? So now, A complement is everything that's in the universe that is not in everything in the universe that is not in the complement. No, that's not in A. So if the universe is 1 through 5 and the set of A is 1, 3, 5, then A complement its set is 2, 4. So the only thing you have to remember about complement is everything that's in the universe that's not in the original set. So if you're asking for the complement of a set, like set A, set B, set C, set D, the complement is always all the elements that are in the universe that is not in the set A, B, C, D, or E. Any questions on this set? Complement set, universal set. Any questions? All right, moving right along, we have subsets. Well, correction. Before we do subsets, we must talk about empty sets. Empty sets simply means there's nothing in them, or the two sets have nothing in common, and usually is denoted with a circle and a line through it, or it's empty. So say, for instance, you have set A one, 2, 3, set B 4, 5, 6. The intersection of B, which is what we're going to talk about in a little bit, would produce an empty set. And the reason being is because the intersection means what numbers in their set do they have in common. And since A has nothing in common with B, they have an empty set. Also, a thing to remember is the complement of a universal set is always an empty set. And the complement of an empty set is always the universal set. So the opposite of the universe, meaning if you have a set numbers of the universe, the complement of that would be nothing. And of course, the complement of an empty set would be everything that's in the universe. So these are typical things that you'll see and you'll be asked about. And literally, if you just remember that the complement of one equals the other, you'll be able to solve all of your set notation equations. Now, next we will deal with subsets. Versus proper subsets. Now, say for instance, A equals 1, 2, 3, 4, 5. And B equals 1, 2, 3, 4, 5. Not only is A and B considered an equal set, but this is considered a subset. Subset, well, set of A is a subset of B, and is usually denoted as A subset symbol, which is a sideways U with a line under it. And so set A is a subset of B if and only if every element of A is also an element of B. So an equal set can also be a subset of between two sets. Also, a set can be a subset of itself if that's the only set that you have. Any questions on subsets? Now, what makes it a proper subset? A proper subset is when the set of A is a subset of B, but it does not equal B, meaning it doesn't have the exact same elements as B. So subset can be an equal set. Proper subsets cannot. So if you have a set A like 1, 2, 3, and B 1, 2, 3, 4, 5, A can be a subset, can be a proper subset of B because A has all of the elements of A are in the set of B, but A does not equal. So remember that proper subsets and subsets, they are different. Subsets has equal sets, meaning all the elements of A could be exactly all the elements of B. Whereas a proper subset, all the elements of A can be inside of the subset of B, but it must not equal B. So as you can see, a proper subset is I have 1, 2, 3, 4, 5 in B. I have 1, 2, 3 in A. Proper subset says A is a proper subset of B because A elements, meaning everything that's in A, is also in B, but A does not equal B. Therefore, it is considered a proper subset. Any questions on the sub versus proper? All right, moving on to intersection and union sets. The intersection of set A and B, which is usually denoted or written as A. I call this my little horseshoe or arch, B. And the intersection of A and B is the common elements between both A and B. So say for instance, A equals 1, 2, 3, 4, 5, and B equals 2, 4, 6, 8, 10. The numbers that they have in common is 2 and 4. So the intersection of A and B are 2 and 4. The numbers they have in common in each set. They both have 2, they both have 4. Therefore, the common or intersection is 2 and 4. Now, the union of this intersection the union of these two sets. Typically, it is a set with the letter U and the second set. It is always written like this. So the union, if you have guessed it already, if the intersection is what they have in common, the union is what they have all together. So the union of A and B is 1, 2, 3, 4, 5, 6, 8, 10. And as you can see with our numbers, the union is everything that's in A and everything that's in B put together without repeating. Now you're going to see different types of request of your set, and usually it's based off of the Venn diagram. Also, I need to make a quick correction when it comes to universe. The universe states here, and typically so now the universe actually is everything. This is considered all the universe. Now the complement is everything that's in the universe that is not in that set. So say for instance you have A and B. The union of A and B is all of A and all of B, but not the universe. That is the union. The intersection is where they meet, where they cross up at. This part is considered the intersection. The complement of A or B is everything that's in the universe that's not in. So say for instance, I want the complement of A. You're going to see a lot of shading of B, except for the intersection of B. All of A will be empty. And everything that's out here that's not in A or B, but still part of the universe. So the complement is everything except this. Now, you're going to see things like A union, B complement. So AUB complement means everything except the union of A and B. That means all of this will be shaded, and A and B will be empty, meaning it won't be shaded, it won't have any, it will be a blank space. And the intersection would be a blank space too, because the complement of their union is everything that is not in the union. Now, the intersection complement, everything will be shaded except, of course, the intersection. The intersection is going to be blank. So that means all your answers fall within the universal set that's not in A or B. The pieces that are in A that are not in B, and vice versa, meaning the intersection. The intersection is the piece that you will not include when you're trying to find the complement of their intersection. That's really all that means. Now, there are some properties in sets, just like there's properties in all of our mathematical functions. But you may recognize some of these properties from our original operation sets, such as addition and multiplication. So we have commutative property of intersections and unions. We have associative property of intersection and unions. And we have distributive property of intersection over union and vice versa. So first thing we have is the commutative property. If you remember, commutative property says A plus B is the same as B plus A. Well, commutative property when it comes to intersections says that A intersecting B is the same as B intersecting A. Same thing with the union. A union with B is the same thing as B union with A. You will get the exact same answer whether you do A to B or B to A. Commutative property. Then you have the associative property, which is basically our grouping property. And you take it and say, for instance, you know that parenthesis A plus B plus C is the same as saying A plus parenthesis B plus C. This same rule applies for when you're doing intersections and unions. So now, parenthesis, set A union with set B, which is union with set C, is the same thing as saying A union with parenthesis, the union of B and C. Intersection rule also applies. The intersection AB intersected with the set of C is the same thing as saying the set of A is intersecting with the intersection of B and C. Distributive property with intersection over union or union over intersection. If you remember, distributive property is originally A times B plus C. That means A times B and A times B is added to A times C. Same concept applies when it comes to the union over intersection and the intersection over the union. So for intersection over union, you have A intersecting the union of B and C, which means the intersection of B of A and B is union with the intersection of A and C. Also, union over intersection, where A is union with the intersection of B and C. All I'm doing is distributing, like I did here and here. Same thing goes here and here. All that means is the union of A, B is intersecting with the union of A and C. And what that simply means is the union of A, the common set between the union of A and the union of B. Also, with the intersection over union, all that means is taking the intersection of A and B and putting it all the elements of the intersection of A and B and all the elements of the intersection of A and C and putting them all together. Any questions on sets notation? All right, guys, this is really all I had for today as far as geometry and set notations. So, of course, since this is all we have for today, if you have any questions as far as math is concerned, other than geometry or what we learned today, you can comment that below. Miss Chris is here to help with all of your mathematical needs. Other than that, I hope you are having a fantastic and wonderful Tuesday. And thank you for tuning in. Also, if you are just now tuning in and you are needing the lesson that we learned for today, you can click on the YouTube link, Facebookers, that is listed in our Facebook description. Once you click on that link or copy that link and paste it into your information, once you click on that link, you can either double tap to the left or you can take the red button and scrub to the left and it'll allow you to review what we learned today. Of course, if you have any questions while we're live currently, you can comment them below. I am here to help, and thank you for tuning in today. All right, ladies and gents, if we do not have any questions for today's lesson, I will see you beautiful people tomorrow. All right, beautiful class. So, this week we will finish on, of course, Friday. We have Wednesday and off Thursday, back on Friday. I will be in on Saturday, briefly, but I will be in on Saturday. Of course, Saturday is for tutoring purpose. Of course, if you have any questions, you can IM me or DM me. If you have any questions about the live or what we learned, once this live ends, you can rewind and review. It will be on my Facebook as well as my YouTube page. If you have any questions outside of the live and you have reviewed the live, you can inbox me, you can IM me, you can DM me, you can also text me at 205 542 5062. 205 542 5062. Again, this is Miss Chris, and I hope you had a fantastic and terrific Tuesday. All we're doing this week is going through the basics and key concepts of geometry. We will get through all of this together. And guess what? I'm so proud of you because you can do this. You can do this because you have done this before. And even if you haven't, guess what? You have been building up to this point. All your math leads to this road. So, congratulations to you. I'm so proud of you. And again, you know how to reach me, you know how to find me. Glad you were able to tune in for this evening. My name is Miss Chris of Mathematics for You Tutorial Services, where we are changing mindsets one problem at a time. Have a blessed evening. I'll see you tomorrow, 5 p.m. sharp. Do not be late now. Have a good one. Good night.